Hey guys, hello everyone. Welcome to Rasayan Academy, all of you. So you have given the CSIR NET examination, many of you, and the examination is over. The response sheet was out. You have also seen the answers. For those students who have already given the examination, it's you have got the answer keys already, so you know which is the correct answer, which is not. And by now we have had a lot of discussion in the group as well as in the classes also that what is the correct answer, what's not. So the I am presenting you some of the questions of section B, selected question discussion we are going to do over here, mostly of the organic and inorganic section, right? And this is for those students who were not able to or who have not given the examination, and also for those students who are looking for proper solutions to the question. Okay. Now, before moving onwards, guys, I will inform you about something very, very important that whenever you are looking for any source of a question, that is, you are looking for a reference. Let's say a lot of students are confused about the structures of some of the molecule. What are you going to do? You are just going to visit scholar.google.com. Okay, you're just going to visit this website, and over here you are just going to put in the name of whatever you want to search. You will get a lot of research papers on it. Okay, so you are not going to be confused about where to get the reference from. You are CSIR NET examination candidates. Okay, you must know where to get references from. Okay, scholar.google.com. So everything that you are confused about, you are going to get some research paper on that topic in this on this website, right? So just open the website and just put in the keyword. You are going to get whatever you want, right? Chalo, so we are going to move onwards and we are going to discuss some really important questions of section B. More in the next video, I'll also discuss some questions of section C as well. So let's start, guys. Now the first question, guys, question ID 82. The geometry around tellurium in the symmetric trimeric species of TeO2F minus is. Now when you once again visit scholar.google.com and you just directly put in the formula of this species, you are going to get another research paper on this, and exactly it mentions trimeric species of KTeO2F. Okay, so trimeric species of this molecule, and in that research paper you will see it is pseudo trigonal bipyramidal. Okay, so I'm not giving you any particular reference for anything because there are so many questions for which we have to give reference. You are just going to search it by yourself. It is not too difficult. Just visit scholar.google.com and you can directly search this over there. Okay, so the correct answer is trigonal bipyramidal and not tetrahedral or octahedral anything. No. Pseudo trigonal bipyramidal was mentioned for this complex, and you will be able to study a lot of other things about this particular molecule in the same research paper, trimeric species of this particular molecule, right? How it is generated and how the structure has been defined based on the X-ray crystallographic studies and so on, right? So we move onwards and we see another important question, ID 90. An octahedral D6 complex has a single spin allowed absorption band. That is a D6 complex, guys. So you know already that D1, D4, D6 and D9 species. All of these are going to have the capital D spectroscopic term, and they are going to have the D term split in this way. Alright, so this is your D term. For example, it is going to split only in this way. For D1 and D6, you know the Orgel diagram, it is going to split into T2G and EG like this. So there is only one transition over here. Alright, so spin only magnetic moment and electronic transition for this complex is. So it is mentioned that it's a D6 complex. It has only one single spin allowed absorption band. So what is the spin only magnetic moment and the electronic transition? That is asked. Okay, so yes guys, how is it possible? D1 and D6 octahedral, if we are talking about, this is D1 and D6 octahedral, this is going to be D1 and D6 tetrahedral on this side. So it's going to be EG and Or let's say, since it is tetrahedral, we just cancel the G, we just write E and this we write T2. Okay, so for the D6 octahedral, Orgel diagram is considered for high spin, so I'm considering D6 high spin. Okay, so for the D6, we see the electron transition will be from T2G to EG like this, and since you are having only you are having 4 unpaired electrons, it is going to be 5. 2s plus 1 value is going to be 4 plus 1, that is unpaired electron plus 1 is equals to 5. So 5 T2G2, 5 EG is going to be the transition, and the spin only magnetic moment is going to be for 4 electrons. So it is going to be 4.9 something, right? So you have the correct answer 4.9 and 5 T2G2, 5 EG. This is the transition. It was a very, very simple question. This is the correct answer. Moving onward now, question ID 85. This question is directly taken from B.D. Gupta. Okay, and you can just check it out, 18 electron rule chapter. Alright, it is the first few chapter, 18 electron rule. From the back questions of the book, this question is taken. In the solid state, the stable structure of metacluster is. So whenever you see something like this, the stable structure means where each rhodium follows 18 electron rule, where each rhodium follows 18 electron rule. So first of all, the stable structure means the complex follows 18 electron rule. You can find out the metal-metal bond. Okay, you can find out the number of metal-metal bonds over here. That's going to be easy. Number of metal-metal bond will come out 3 when you are just trying to calculate the whole of this. So ruthenium has how many electrons? It has 8 electrons. So 8 into 3, 24, plus 2 into 10 is 20, plus phosphine gives 2 electrons, so 2 into 2 is 4. So 24 plus 24 is 48. Alright, so 18 into 3 minus 48 whole divide by 2. 54 minus 48 divided by 2, that gives you 60, 6 divided by 2 is equals to 3. So you're having 3 metal-metal bond, and just by that you confirm that this is the correct structure. But anyways, we will see that one ruthenium has 8 electron and each metal-metal bond gives it 1 electron, 1 electron each. So ruthenium has 8 electron, carbonyl has 2 electron, phosphine has 2 electrons. So how many per ruthenium? Let's check. 8 plus 2 10 plus 2 12 plus 2 14 plus 2 16 and 17 and 18. Once again, this ruthenium 8 electrons plus 2 10 plus 2 12 14 16 17 and 18. For this ruthenium 8 plus 2 from the metal-metal bond, so 10, and once again you are having 4 carbonyls, so it is going to be 18. So this complex has 18 electrons per each ruthenium, so it's the stable compound. Moving onward, question ID 91. Consider the following statement about infrared spectroscopy. Now the thing is, there are 4 options, A, B, C and D. Which one is correct? That is asked, right? So it is used to determine the band gap, the band structure and the charge carrier concentration of a compound. So for a particular compound, these things are not discussed through the IR. They might be discussed from the UV visible spectroscopy, but not from the IR spectroscopy. Okay, right? Because IR is basically used for identification of the functional group. This is correct. Used for the identification of the functional group of a compound. It is used to characterize different stretching and bending modes of vibration in a molecule. This is also correct because stretching frequency comes towards more towards the 4000, bending vibration comes toward the fingerprint region. Heteronuclear diatomic molecule are IR active. Heteronuclear diatomic molecules like CO, like NO. They are NMR, they are IR active because they have a dipole moment. Okay, so answer A, B, C and D are correct. A is incorrect and that is the correct option. B, C and D are correct. Question number 92. This was also a very simple question from radioactivity for the following nuclear decay series segment. So 234 changes to 230 and 90 is still 90. What are you going to do from all of these combination? 1 beta, 1 alpha and 1 neutron, 2 beta and 1 alpha, 3 beta, 2 beta and 1 neutron. So basically guys, when you are emitting 2 beta from here, alright, so beta particle is basically 0 and -1, so that you are changing, you are adding to it, you are adding +1 to it. So if you are adding 2 beta, if you are emitting 2 beta from here, the mass is going to reduce, the mass is going to be as it is 234, and this is going to be 92. 2 is going to be added to this, and when you eliminate 1 alpha, so 2 beta adds the mass and 1 alpha eliminated is going to eliminate 4 from here and this 2 from here, so it's going to give you 230 and 90. So you finally result into this, so you just have to try out different combinations. This is the correct one, 2 beta and 1 alpha. It was a very simple question. Question ID 81. The known oxidation states of europium in the aqueous solution are. Now, europium and ytterbium are two of the elements of the actinide series that have the half-filled and the full-filled configuration. 4F7, 6S2 and 4F14, 6S2. So you must know guys, only these two specifically are going to show you +2 oxidation state, and +3 to फिर it is the common oxidation state of the whole group, but here these two are also going to show +2. So +2 and +3 is the correct answer for europium. Okay. The proton NMR spectrum of C5H5 whole twice FeCO whole 2 exhibits two peaks of equal intensity at room temperature, but four resonances of relative intensities at lower temperature. Hapticities of the C5H5 are. Now guys, these kind of questions are very nicely given in BD Gupta. Okay, so I would suggest all of you to just do these questions from that book. You will have a very good clarity on it. Now the proton NMR spectrum, guys, first of all, when these type of questions appear, you are just going to ask yourself that if I'm taking, first of all, let's count the number of electrons. Let's say if I'm taking both of the rings to be eta 5, how many number of electrons would be there? So eta 5 and eta 5 will give you 10 electron plus 8 from the iron plus 4 from the carbonyl. This is going to be 22 electrons. You don't want 22 electron, you want 18 electrons. So which means that from the 18 electron you can say both of them will not be eta 5. Let's say I'm making eta 1 and eta 5. Then plus 8 for the carbonyl, plus 4, plus 8 from the iron and 4 from the carbonyl. So how much do you have? You will have 5 plus 5. Yes, you will have 18. Then you try out eta 3 and eta 3 plus 8 plus 4. You are going to have 6 plus 4 is 10 and 18 once again. So let's check what is the correct answer. Eta 3 and eta 1 is not possible. You're not going to have 18 electron rule followed. Eta 5 and eta 3 will also give you extra electron. It could be eta 5, eta 1 or eta 3 and eta 3 as well. So let's check out now from the values. Okay. Now we can just see from the proton NMR values after doing the electronic calculation. Yes, let's see. So what is given over here? That is, yes, exhibit two peaks equal intensity at room temperature. So at room temperature, if I am having eta 3 and eta 3, both of them will give me one peak. Okay, because both of the rings are same. If I have eta 3 at room temperature, guys, please try to understand this. It is going to be the same for both of the rings. Okay, and because of ring whizzing, you will get only one type. But since it is different, see, both of the rings are same over here, and here it is eta 1 Here it is eta 5. Now there are two important concepts that you have to know. At room temperature, even if I am getting only two peaks of equal intensity, which means I am getting equal intensity peak, means that eta 5, guys, eta 5 means the center is at one ring. The bond is with the pi electrons, okay, in this eta 5 ring. Okay, 5 electrons. So the ring can actually rotate around like this, which is known as ring whizzing. So this concept is known as ring whizzing, and because of that all the 5 carbons will appear the same. However, what happens over here, here it is connected to just one carbon, and the rest of the hydrogen should be different, but this is also appearing as the same because this, due to the fluxional property, right, what happens is the ring is going to change its shape, or basically the coordination site, from here to here to here to here to here, right? So that is also ring whizzing, but changing the hapticity. Eta 1 remains the same, but from different carbons it is going to donate at room temperature. That is why you are having same but two different peaks for eta 1 and for eta 5. And when we take it low temperature, what happens it? Four resonances of relative intensity 5221. Now what happens? This 5 is for the eta 5, and 2, let's say I'm writing H1, H1, H2, H2, and this is the H3. So H1 is to H2 is to H3 is going to be 2 is to 2 is to 1 for this ring. Okay, this part is for this ring and 5 is for the CP. So you confirm the structure, it is eta 5 and eta 1. Right, next question, 88 question. The ionization energy, alright, of S or P block element are given below. Now it's a very simple question, guys, that when there is a very high jump in the ionization energy, which means you are removing an electron from the fulfilled orbital. Okay, so if I say I have NS2 and NP1, so if I remove this one electron is going to be lower energy, and when I remove an electron from NS2, this one electron is going to require very high energy. Okay, so the number of valence electrons are asked. Alright, so look at this, guys. X is having 1086, that's a 4-digit number. Then 2353, 4620, 6223, and then a direct jump to 1, 2, 3, 4, 5-digit number, which means that you are having 4 electrons in the P shell maybe, and this electron was there in the S shell, something like this. Because when you have completely removed the 4 electrons, you are going to the S electron, which is going to require a lot of high energy. You have 4 valence electrons in X. Similarly, what about Y? 800, it was 3-digit number, and then you are having 24274 digit, 30604 digit, and 5 digit over here. So you can say that Y is going to have 3 unpaired electrons, 3 valence electrons, because now the value is too high. 496, and directly jump to 4. See, this 400 something, this is a direct jump to 4000 something. You are clearly going to see that it is having only one unpaired electron because the energy jump is too high, higher than the Y also. So you have only one unpaired valence electron over here. So this is your answer. X equals to 4, Y equals to 3, and Z equals to 1, right? This is a purely aptitude type question, right? Purely based on logic. So what is the order of decreasing carbonyl stretching frequencies in the following species A to D? Now guys, you can purely answer this question based on logic. Okay, why? Because you know that all of these, if you see these three, these are going to be somewhat isoelectronic species, and you are just changing the charges on all of these. Okay, so manganese being a third row element, okay, it is going to have slightly better pi back bonding as compared to osmium and iridium, and also the charge is less on manganese. Okay, yes, so you can say without any doubt that iridium having a 3 plus charge has a greater carbonyl stretching frequency than osmium having a 2 plus charge as compared to manganese having a plus charge. So this you can answer based on logic. That is not a problem. Isoelectronic species. But what about the carbonyl, guys? We need some reference for this. Okay, so we have the reference over here, guys. Once again, I just visited scholar.google.com and I got a paper on this structure and bonding of isoelectronic hexacarbonyls. Okay, so what did I find? I found so many different molecules which are compared, and our question has these two. Okay, our question has these two. So let's see what is important. You can just study the whole paragraph. You can just visit this paper also. All right. The title goes like this. You can just visit it and you see something over here. The CDA method shows a regular decrease of metal carbonyl pi back donation from hafnium 2 minus complex to iridium 3 plus complex. Okay. And one very important line, the carbonyl bond of this complex is shorter than in the free carbonyl. And how is that going to happen? Yes, this is very, very important that the carbonyl bond of iridium complex is shorter than the free carbonyl, which means that the carbonyl stretching frequency of iridium complex is going to be higher than the free carbonyl because the bond is shorter. Pi back bonding is not there at all. Okay, so this is going to be shorter than the free carbonyl. You can read the whole paragraph, guys. It is up to you. So, uh, yes, for the hafnium gives a smooth curve from the equilibrium value, which is longer than in the free carbonyl. So obviously it is going to be longer because the hafnium has a 2 minus charge and iridium has a 3 plus charge. So this is the evidence. You can read out the whole paper that in what context it is talking about, how it is comparing all the values, right? But here we see the carbonyl bond of iridium is shorter than in the free carbonyl and hence a higher stretching frequency. Okay, and if you look for the exact values of these complexes, then also you will be able to find those exact values. Okay, so that's not a problem. Free carbonyl is going to have a lesser value than iridium, all right, and even lesser value with osmium also. So C is greater than B, which is greater than D and A. You can check it out on the same source, guys, and this is the correct option without any doubt. Moving onwards, ID 93. In the stratosphere, the radical produced from chlorofluorocarbon reacts with ozone as follows. So you will see that what is this reaction? Cl radical plus ozone. You know how it is going to break down. It forms a ClO radical plus O2 gas. Colorless gas is O2 because ozone is blue in color. Now 2 of this X, matlab ki 2 of the ClO radical is going to combine to give you X2 without any change, ClO whole twice. Okay. Now this X2 is going to eliminate a Cl radical. What else remains? ClO2 remains. But this ClO2 is not going to be like this. Not at all. It is going to be like this. How do you know that? You know that because this molecule is not a simple molecule, it is a peroxy radical. And when the peroxy radical breaks like this, it is going to generate one more free Cl2 radical. Alright, and the chain goes on. You see, this is the last product and this is used up in destroying another molecule of ozone. So this is a repetitive process. This is how Cl radicals are destroying ozone. So absolutely, this is a peroxy linkage and it is not like this. Don't be confused about it. This is correct. Alright. So yeah, simple question. X and Y respectively are. So X is this and Y is this. Moving onwards, among all of these, the compounds with the highest conductivity is. Now, in this question, which conductivity it is talking about? Most probably electrical conductivity. And guys, rather than searching on Google, please search on scholar.google.com where you have actual research telling you that how you can compare or what measures have been taken to compare the electrical conductivity or thermal conductivity of all of these molecules. This is the correct answer, absolutely. All right, a polymer of sulfur and nitrogen. Now, very simple question, guys. ID 86, the number of moles of magnesium ATP needed for the reduction of 1 mole of nitrogen by nitrogenase enzyme. Now, for this question, if you just remember this equation, yes, in the examination, if you remember this equation, it will be really great because this has already been asked in one of your previous year papers. Okay, so 8 moles of acid, 8 electrons and 16 ATP molecules are used up to the conversion of nitrogen to ammonia, and this is how it is: ADP plus 16 phosphate ions. So correct answer 16. Question ID 118. The intermediates involved in the given transformation are. Now, guys, this question is not very difficult, a little bit confusing though, but not difficult. What is being asked that in the presence of a base, you are getting the dimer of this molecule. And how are you going to get that? If you try to substitute this chlorine with OH minus, you are going to get O minus, which is not correct. And if this O minus attacks on another molecule of this, you are going to end up with some ether, which you are not forming. So that is why the OH minus is not there to remove a chlorine. It is there to remove a proton. It is more of the E1CB type reaction. Why? Because there is a nitro on the para position. So you are actually having a negative charge. This is going to attack This is going to attack over another molecule like this that ends up in option number B. Now further OH minus is going to undergo E1CB elimination because there is a nitro molecule electron withdrawing group. So it is going to undergo E1CB elimination, gives you this answer. So A and B are both correct. This is the correct answer, A and B. Moving onward, ID 109, which of the following species are aromatic in nature? Now guys, many of the students are getting confused about this. Why? Because here it looks like that nitrogen is having a positive charge. It is not possible. Guys, look at the species properly. You are only having two bonds on nitrogen. You are only having two bonds on nitrogen. It is not like pyridine. There is no third bond. So I can have a positive charge on nitrogen. This is just going to be like tropylium cation, and you are having only 6 pi electrons to delocalize. Okay. So one of the resonating structure is going to be like this. Okay, positive charge over here. This is just like your tropylium cation, where you are having 7 carbons but only 6 pi electrons. So this is aromatic. Second one, look over here. Now when we are using the electrons of sulfur like this, so how many electrons in total? 1, 2, 3, 4 and 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 pi electrons which can completely undergo conjugation. Alright, so it is going to be aromatic, follows the Huckel's number. What about option number C, guys? In option number C, we are not going to compare this by Huckel's method. We are just going to see it from the Craig's rule. So what does the Craig's rule say? Craig's rule says that when you want to check for non-benzenoid polycyclic system, you are first of all going to see if there is a C2 axis. Yes, there is a C2 axis. Now check out the number of pi bonds. 1, 2, 3, 4, 5, 6. Number of pi bonds is equals to 6. That we write as n. So if n minus 1 is odd and if n minus 1 is even, we have two different conditions. Okay, so n minus 1 is odd, we are having a non-aromatic compound. If n minus 1 is even, we have a aromatic compound. Okay, So number of pi bonds is equals to 6. First we check a C2 axis. Here C2 axis, then we will proceed. 1, 2, 3, 4 and 5, 6. Number of pi bonds is 6, that is n. N minus 1 is equals to 5. If it is odd, then the system is non-aromatic. So our answer is only A and B are aromatic. This is followed from the Craig's rule of aromaticity for the non-benzenoid system. Okay. Moving onward, 107. The following reaction sequence is an example of. So it's a very direct question, guys. Very simple question. That is, we are getting B from A from some source. We are getting D from C from some source. And we are combining B and D to make a target molecule. So looks like that both of these are converging down to transition to the target molecule. So we call it the convergent synthesis, isn't it? It's not a linear synthesis. Linear synthesis is what we do all the time. A plus B gives C plus D. Okay, diverted synthesis and diverted is different. Divergent synthesis would be like this. That from one molecule we are getting two different molecules, right? Something like that. But this is convergent because from two different sources we are creating our target molecule, and that these two different sources we have got from other sources, right? So this is convergent synthesis, absolutely without any doubt. Another easy question, ID 116. The structure that corresponds to the following proton NMR spectral data is. What is the data? 1H NMR 3.64, 6 hydrogens 3.64. Okay. 2.04 doublet of a doublet, 2 hydrogen, 1.62 triplet doublet, 1 hydrogen, 1.20. So guys, when you have so many molecules to look at, you are going to first confirm the OME. That is, you must have an OCH3 methyl, because that only is going to be 3.64 value, and also singlet. And this we have already discussed plenty of times, that singlet 3.64 is only obtainable when you are having a methoxy. So that methoxy is not possible when you are having OCOMe, because it is going to be like this. That carbon, that methyl is connected to carbon. It could be a singlet, but it would not be such a high value. So just do wrong. Option number, let's say C and D, B and D, sorry. Now what happens with these two? Here you have a sigma plane, here you have a C2 axis. So looks like both of the hydrogens over here, are going to have the same value, isn't it? Yes, looks like I'm drawing it over here, guys. It's a very precious question. CO2Me. So both of the methoxys over here, let's say 6 hydrogens collectively, possible only when we are having COMe. This is sorted out. Now this hydrogen, these two hydrogens, you are going to have close to these two. Alright, so these should be a triplet. They should have been a triplet because they are surrounded by two hydrogens over here and one hydrogen over here, neighbor. So it should have been a doublet of a triplet. But do we have a doublet of a triplet? No, we have a doublet, triplet, doublet, and yes, triplet, doublet once again. So let's see further. If we have these two hydrogens different, let's say this is H1, let's say this is H2, then H1 is going to split this hydrogen into a doublet, and H2 will also split this hydrogen into a doublet. Now it is going to become doublet of a doublet, which means these two are diastereotopic protons. Diastereotopic hydrogens separately will split both of these hydrogen into a doublet. Now this hydrogen also will be split by these two into a doublet, and you have two hydrogens for doublet, which is very important. It's going to be 2.02 for both of these. Okay, yes, and 1.62 triplet doublet. So 1.62 is going to be for this diastereotopic protons, because they are having a lesser value and they are split by these two hydrogens collectively, because these hydrogens are enantiotopic, right? You have a sigma plane over here. These two hydrogens are enantiotopic. They will be taken together for splitting this one. So split by 2 will give you a triplet. Split by the geminal one will give you a doublet. So you can write triplet, doublet, or doublet, triplet, whichever. Okay. The same for this H1 and H2. For H2 also, these two hydrogens are collectively taken for splitting. Two hydrogen will give you a triplet and the geminal hydrogen will give you a doublet. So once again, triplet, doublet. It is so important to recognize this, that I'm erasing everything, that the difference in these two structure is that if you are considering, or let's say we write the molecule like this to be to understand better. CO2Me, one hydrogen, CO2Me, another hydrogen. If you are considering this structure where there is a sigma plane cutting through the molecule like this H and this H will be the same. However, this is H1 and this is H2, diastereotopic. So only possible in this option number 1. If you consider the next structure, what you'll have is CO2Me and CO2Me is below. So this hydrogen and this hydrogen, they are C2 exchangeable. Along with that, this hydrogen H1 and H2 are also C2 exchangeable. So you will not have a diastereotopic proton in this. This is going to be wrong. This is the correct answer, option A. Another beautiful question, guys. ID 114. Correct IUPAC name of the following compound is. So it's very easy, guys. You just have to find out the E and Z nomenclature over here. Okay, other than that, it's a very simple question. So see, it is 1, 2, 3, and 4 and 5, 4 and 5. So obviously we are going to go with the largest chain which has the double bond. Alright, so you are going to have this as the substituent. Why? It's just a chloromethyl group and the double bond is there in the chain absolutely. Okay, so this is going to be the longest chain. So 3 chloromethyl, okay, yes, that's common in all of these, fine. 3 chloromethyl, but yes, where is the E and Z nomenclature? Let's see that. Okay, so on the second carbon, 1, 2, 3, on the third carbon, what is the nomenclature? First priority goes to this carbonyl. According to the CIP rules, you will give the E and Z nomenclature, right? So first priority to the, yes, first priority to this, second priority to this, or let's say this is connected to an oxygen and this is connected to an bigger size Cl over here. So let's just keep it. First priority to this and second priority to this. Similarly, first priority to this, second to this. Because we are following the CIP rules where the priority is given first of all based on the atomic mass. Nothing else. So Cl has a greater atomic mass than oxygen and the central one is a carbon. So it's going to be a Z alkane. Very, very simple. Okay. Z, third, 3 chloromethyl, pentane, 3, pent 3 ene and 2 on, like that. So this is the correct answer based on the IUPAC. Next question, ID 112. Following reaction involves. Now guys, you will see that there is ring closure on these two positions. First of all, we will see that how many number of electrons are involved. Okay, first see that. So let's say if we do the ring closure over here, we are going to not only have 6 pi electron, but all the electrons involved. So 1, 2, 3, 4, 5. 5 bonds, 5 into 2 is 10 pi electrons are involved. 10 pi electrons are involved. 6 is the wrong answer. Okay. Then we are going to write down what will be the stereochemistry. Now you see this hydrogen and this hydrogen, they are opposite to each other, and they hydrogens, they finally end up together. Okay, so these hydrogens which are opposite, they finally end up together. So how the process is going to be? Guys, 10 pi electron classifies into 4 into 2 plus 4n plus 2 pi electron system, right? 4n plus 2 pi, photochemical, conrotatory, and 4n plus 2 thermal disrotatory motion. This is the rule from the Woodward-Hoffman rule, right? So 4 into 2 plus 2 gives you 8 plus 2, 10 pi electrons. Okay, right. So we are confirmed it is 4n plus 2. We just have to check conrotatory or disrotatory. So guys, when the hydrogens are opposite to each other, and if they are moving in the thermal condition, okay, that is, these are opposite and we are doing the disrotatory motion, they are going to end up cis. So from the ODC rule, you can directly say opposite disrotatory motion, they are going to end up cis. So we have the hydrogen cis, we are going to do a disrotatory motion in the thermal 10 pi electron cyclization. So answer is option number C. Okay. Next question, guys, ID 119. Correct order for the magnitude of heat of formation. Now this is important and confusing. You have different heats being asked. Heat of hydration, heat of formation. All of these things are very important. So heat of formation, if it is high for any molecule, if the heat of formation is high, which means the stability is also high. High stability for heat of formation. Heat of hydrogenation, the stability will be different, but here heat of formation is high, stability will be high. So here you see adamantane, most symmetric structure, and here the strain is minimum. Then you have B and C, guys. So A is going to be absolutely more stable because it has the minimum strain. In option number C also you will have you will have less strain as compared to B. Here you are having this Norbornene. This is having more strain than C, and that is why the heat of formation or the stability will be less as compared to C. So A is maximum, then C, and then B. This is your correct answer. Alright, next important question, guys. The number of signals observed in the proton decoupled C13 NMR spectrum of the following compound is. Now, it is so simple, guys. You just have to see the symmetry, number of signals observed. So look over here, you are having a C5 axis. How do I know a C5? Because I just saw the central portion. If I just move on with 72 degrees, this much, I'm going to get the same structure. Alright, so basically 360 degree divided by 5 is going to give you the angle which you are going to move, and that is going to give you the same structure. Yes, 72 degrees basically. That is the internal angle of pentagon. Alright, so all of these 5 carbons will be the same. Okay, which means how many carbons are same over here? These 5 carbons are all the same. So one signal for this. These 5 carbons, these different carbons will also be the same. So one more structure for this, one more signal for this. One carbon over here, another over here. These two are also same. So one more signal for this. And all of these are same. Now the outer ones. So you're only going to get 3 different signals. Okay. One for this one for this. Okay, I'm just mentioning once again. One signal for this type of carbon, one for this, and one for this. These 3 are going to repeat. Only 3 signals. Moving onwards, ID 113, guys. The major product formed in the following reaction is Now, if you have studied from chapter number 27 in Claydon, you will know that whenever sulfur compound has a negative charge like this, guys, sulfur itself can hold the negative charge like this, and its resonance structure is like this. It is not like the carbonyl. It could be correct in this way also. Both of these resonating structures are correct. Oxygen can attack as well as sulfur can attack from its lone pair. Alright. So, looking at this molecule, the carbon over here is a soft carbon. It is not a hard center. It is a soft center. So who is going to attack? Sulfur is going to attack, and that is why this is your answer. Sulfur has attacked, not the oxygen. This is absolutely wrong. You are not doing the elimination of any kind. It is not a strong base. It's a nucleophile. So this is your correct answer. Chapter number 27, sulfur, selenium, and phosphorus chemistry. Okay. All right, guys. So I have discussed so many questions with all of you, and I think that you find these questions, find the solutions relevant. Please visit the same source, scholar.google.com, for finding out different research papers on whichever reference you want to find. And I'm going to see you all in another video where we are going to discuss questions from section C of the recent exam as well. Take care, all of you. And if you are liking the session, please give it a thumbs up. Please also subscribe to the channel for more preparation videos. And take care of yourself, guys. Bye, guys.